We're now going to talk about phases of matter because it's good to formally introduce that. I think we actually talked a lot about what I want to cover here in the last section, but I want to represent the information a little bit differently. This chart on the bottom right should not surprise you. Okay, melting and freezing, sublimation and deposition. I always forget deposition. Condensation and evaporation. And we can go between all three. We'll talk about why as we go. Who hasn't seen the sublimation of CO2 solid crystals? Hasn't seen? Who has seen the sublimation of solid crystals of CO2? Yeah? Where? Where do you get exposed to that? Dry ice. Yes. So that's exactly what I'm talking about. Yeah, so you can buy dry ice, which is solid CO2, and it sublimates. It doesn't become a liquid before it becomes a gas. It hurts because it's cold. Don't pick it up. Solids, liquids, and gases. We all were. And some of us still are. No. Solids, liquids, and gases. So this is trying to represent molecular level. So solids, everything's crystalline and ordered and so forth. We will call that, for our purposes, incompressible. You can compress it a little bit, but really not very much. Liquids, so you can see the molecules are a little further apart. That's true in everything except water, unfortunately. Well, fortunately for a bunch of reasons. Liquids tend to stay together. They're attracted, all right? But everything moves freely. They take the shape of the container in which they're put. Gas, the molecules are very far apart. Density is low. It will fill the whole container, not just fill the lower end of a shape. And gases are compressible, so we can bring the molecules closer together. There's lots of free space between them. And rarefy them, we can move the molecules further apart. The reason that substances tend to exist in these forms is that, unlike the ideal gas equation purports, that molecules are actually attracted to each other, like molecules are attracted to each other. And what we find is that if there was no thermal energy, so there's no movement, right, things would become solids. And because they have that tendency to stick together. And we find that we actually need thermal energy. If you're happy to think from 0 Kelvin and think up, right, you actually need thermal energy to break those bonds, okay? And that's the point at which they escape, the molecules escape that particularly liquid phase, right? They escape and become gaseous. When we talk about temperature, we tend to think of temperature as being like a fixed point. So if you said that something was 20 degrees C, then all of the molecules are at 20 degrees C. But we know that temperature is a macroscopic measurement. The individual molecules have energy. They don't actually have temperature in and of themselves. And indeed, if we looked at the number of molecules, that's an N. Let me get that. Ooh, that's an N, all right? The number of molecules that are at some given energy, we actually find that we get a distribution around some median point, okay? And so some of the molecules have got a little bit less energy, so they're off to the left. Some of the molecules have got a little bit more energy, they're off to the right. And when a high energy molecule bumps into a low energy molecule, they might swap. One becomes lower, one becomes higher. And over time, this distribution doesn't tend towards a point. It actually tends towards the distribution. This is called thermal equilibrium, and you have some distribution. I think it's called Boltzmann's distribution, but that might be just for gases. I don't know whether he also does liquids. So some of these bonds, right, if you had some threshold energy required, so this is a liquid, if you had some threshold energy required for molecules to escape from the liquid and become, go into the gas, all right, then these molecules here would all evaporate. So just those very high energy molecules would evaporate and the distribution would shift to the left, okay? And the distribution would shift as molecules evaporate. So evaporation lowers the overall energy in a system, right? So when it evaporates, it gets cold. That's what we think of as cold. Now, what does pressure do in this system? Pressure moves this line. Okay? So at higher pressures, the line moves over here. Okay? At higher pressures, if you've got a liquid, the molecules need more energy to come from a liquid into this gaseous state. And the reason is, so there's already gas above it, otherwise there'd be no pressure, so there's already something going around above it, okay? And the gas is bearing down on the liquid and forcing the molecules to stay in solution, okay? At low pressure, that moves the line over here, moves the line to the left. And we find that it's easier for molecules to go from a liquid state into the gas state, so it's easier for them to evaporate. So this is just a different way of saying the same thing. At higher pressures, liquids boil at a higher temperature, and at lower pressures, liquids boil at a lower temperature. And that boiling takes with it energy, and condensation gives the energy back. So if a molecule from the vapor space, so they're going really fast, they're really rarefied, if that impinges on liquid surface and stays there, then some of that energy that's carrying, because it's going really fast, has to be distributed into the molecules of the liquid. That might be a different molecule will then evaporate and go out into the vapor phase, or it might be that it stays condensed, adds to the mass of the condensation, but the temperature of the condensate has to rise because it's got more internal energy at that point. So just trying to give it to you a couple of different ways. Pressure tends to compress substances. Temperature tends to expand a substance. Ice is almost unique in that when it turns from the liquid phase to the solid phase, it does what? It expands, right? That's very unusual among substances. It has to do with the way that H2O is orientated. And as a liquid, it can go around itself a lot more easily. And as a solid, it has to expand to take up its crystalline form. But that's unusual. So, with the liquid phase to solid phase, transition as well, if you compress a substance, it tends to help it freeze. So if you compress a liquid, it tends to help it freeze, except for water, where if you rarefy it, it helps it freeze, which is also potentially counterintuitive. And we'll see that when we look at the PVT chart. All substances that we deal with have a sublimation pressure. So at low pressures, for example, so liquid ice water, so H2O as ice, will sublimate to H2O at a vapor at very low pressures. For CO2, dry ice, where we get to see that, the pressure above which, so the pressure at which you get liquid CO2 is about 5 atmospheres, I think. So you need a pressure above 5 atmospheres, and then if you had solid CO2, it would melt to become liquid CO2, and if you continued heating it, it would become gaseous CO2, and it wouldn't sublimate. So at high pressures, you can get CO2 to not sublimate. At low pressures, you can get water to sublimate. And it's below 61 pascals, which is a number we've seen before. At an exact pressure and temperature, solids, liquids, and gases all exist. The definition of the Celsius is that water freezes at 0 and it boils at 100 degrees C. That was good enough when Celsius was doing his thing. It's not good enough for us because we know that local atmospheric pressure differences can change that 100. So the Kelvin isn't defined as degrees C plus 274.15. 773.15. Sorry, I've got the critical temperature of water in my. So Celsius is defined as Kelvin plus 273.15 nowadays. Kelvin is defined as 0 Kelvin is no molecular motion. So yeah, because temperatures measure molecular motion, and 273.16 Kelvin is the triple point of water. So Kelvin is defined between absolute 0 and what we'll call the triple point of water. Can we throw up? So, if you can get some point, so it's a high pressure at which a solid becomes a liquid, then becomes a gas, and a low pressure at which a solid just becomes a gas, then you should be able to find an exact pressure and indeed temperature, right? An exact pressure and a temperature at which you could have a solid phase and a liquid phase and a gas phase all in the same container, right? So it's one substance, water, we can take water. So you can get solid water and then liquid water and gaseous water all happening in the same container. It only happens at a very specific pressure and it happens at a specific temperature. The temperature is 0.01 degrees C, 0.01 degrees C or 273.16 Kelvin. All right? And that's how the Kelvin's defined. The Celsius is now defined off the Kelvin. The Fahrenheit's defined off the Celsius. It's dreadful. So, fascinatingly, the triple point of water is above 0 degrees C. And this is because water wants to expand as it freezes. If you compress it, then you prevent it from freezing. So atmospheric pressure prevents water from freezing a little bit. If you rarefy the atmosphere a bit, so you reduce the pressure, it can freeze more easily, meaning that if water freezes at a higher temperature at lower pressures. Only a little bit higher. It's not much, but it's, you know, it's interesting. And that's also why our table stops at 0.01, because below the triple point, we can't use water as a liquid and vapor because it won't exist in the liquid phase. It'll exist in the solid phase and in the vapor phase. Cool. Is anyone surprised by that? Anyone heard that before? Anyone's like, yes, I knew what the triple point was. Good. Physics, chemistry? Physics? Did we do it in physics at this uni? No, that's fine. Good, don't worry. Sorry, not to put you on the spot. At high temperatures, high pressures don't cause condensation, so this is super critical. You can't compress atmospheric air at atmospheric temperatures until it becomes a liquid. It just doesn't condense. That's called a supercritical substance, and the critical point is at the peak of our saturated vapor, saturated liquid line. So we've talked about supercritical substances. That was what I wanted to talk about, phases of matter.